Welcome to Geology 108, Planet Earth. Earth's beginnings take place during a period of extreme violence, dominated by impacts with other bodies orbiting the Sun and extreme weather patterns in Earth's primordial and secondary atmospheres. This period is rightly called the Hadean Aeon, named after the Greek god and ruler of the underworld, Hades. Stars, planets, and moons, formed by the accretion of gas, dust, and debris floating in the original solar nebula. The Sun absorbed 99.9% of the mass of the nebula, and the residual mass coalesced to form the rest of the solar system. The force of gravity and conservation of angular momentum combined to concentrate all the planets along a single plane called the ecliptic. Elsewhere in the universe, many stars orbit alone around their galaxy, not surrounded by any planet. Instead, the solar system features 8 planets and many other moons and dwarf planets. The protoplanet that would become Earth was the largest object to survive in our section of the solar system, roughly 150 million kilometers from the Sun. At the time of its final stages of formation, Earth was a lonely, moonless world that had almost achieved its present size of close to 13 kilometers in diameter and its mass of 6 billion kilograms. Earth is massive enough to have a strong gravitational field that prevents fast-moving water vapor molecules from escaping the planet. If Earth had been as small as Mars or the Moon, it would have been a dry world. Planetary differentiation started to take place, separating out different constituents of Earth's interior as a consequence of their density and chemistry. The denser materials of the planet sunk to the center, and the less dense materials rose to the surface. Planetary accretion and differentiation converted gravitational potential into heat, making even the surface of the planet extremely hot. As the light elements converged to the surface, they formed a magma ocean. Earth's planetary differentiation created a layered structure consisting of metallic inner and outer cores, a silicate-rich mantle, and a crust that concentrates light elements. The inner and outer cores are made of the same metal, combination of iron and nickel. But while the outer core is fluid, the inner core is solid because of the extreme pressures found at the center of the Earth. The newly accreted Earth bore some similarities to our modern planet, but its appearance was radically different from the marbled blue planet that we know. There were no oceans or continents. There wasn't even an atmosphere at first. During Earth's turbulent earliest days, it was a hot, blackened sphere of dense igneous rocks. Really a hellish of a place. Giant impact with Theia, shortly followed by the formation of the Moon, marked the point when the Earth obtained its final mass and composition. Earth's history is marked by many impacts with meteorites, but they don't significantly alter its bulk composition. The giant collision with Theia tilted the Earth's rotation axis by about 23 degrees, producing the conditions for seasons to alternate throughout the year. Interaction with the Moon also helped the Earth to lock into a steady rotation pattern, making the climate more stable over geological timescales. During the Hadean times, the moon was more than 10 times closer to Earth than it is today. The length of day was just 5 hours, and the gravitational pull of the moon created giant tides, perhaps a kilometer high. Earth could not remain airless for long. The terrestrial planets are volatile poor relative to the more distant gas giants, but they are not volatile free. The magma beneath the thickened black crust contained enough water, nitrogen, and carbon to lower the melting points of rock significantly and to decrease its viscosity from that of a thick paste to that of running water. This magma, less dense than its surroundings, exploited cracks and fissures to force its way to the surface. The magma exploded with tremendous force as it breached the surface, releasing vast amounts of water vapor, carbon dioxide, and other gases. What would eventually become the oceans and atmosphere. Gas and water on Earth came from degassing of the crust and mantle during cooling, with some contribution from impacts with comets. The gas emitted by current volcanoes contained 50 to 60% water, 24% carbon dioxide, 13% sulfur dioxide, and 3% other volatiles. The carbon and sulfur dioxide remained in the outer gas layer, forming Earth's secondary atmosphere, a mixture of gas containing no oxygen. After some time, the volcanic water cooled and formed a global ocean. As bodies of water accumulated in larger and larger volumes, water began to shape the surface. Roaring rivers cut deep valleys, while crashing waves ate away at shorelines, producing Earth's first sandy beaches. The first ocean on Earth was a global ocean due to the absence of major topographic features on Earth. Evidence from the most ancient sediments in Jack Hills, Australia, point to the presence of an ocean as far as 4.4 billion years ago, when the Earth was only 150 million years old. You may recall a scene from the movie Interstellar by Christopher Nolan, where the protagonists explore a planet surrounded by shallow water. Later in that scene, they have to rush out as a giant tsunami, perhaps several kilometers high, approaches at great speed. These conditions resemble early Earth, when it was covered by a global ocean and the strong interaction with the moon, very close to Earth at that time, created giant tidal waves. Earth's core is made of conductive metals, and the outer core is fluid. Earth's rotation and the internal convection of the outer core entrains these charged particles. As the motion of any charged particle induces a magnetic field, the circulation of metallic fluids in the outer core creates what we call the geomagnetic field, or the geodynamo. Any magnet aligns with the magnetic field, so perhaps the simplest manifestation of the geomagnetic field is that a compass points north. The Earth acts essentially as a giant magnet. The geomagnetic field extends far outside the atmosphere into outer space in what we call the magnetosphere. The magnetosphere plays an important role to protect the atmosphere from outside interference. Magnetic fields deviate the flow of electrically charged particles, So Earth's magnetic field shields us from most of the charged particles of the solar wind and cosmic rays. The combined effects of the magnetosphere and the Earth's gravitational attraction prevents our atmosphere from vanishing into outer space. Hence, Earth's secondary atmosphere remains stable for 1.5 billion years. Today's ozone layer, which protects the Earth from harmful ultraviolet radiation, would disappear without the protective magnetosphere. We know the age of the Earth based on radiogenic dating, a technique that uses the relative concentration of isotopes and their known constant rate of decay to date rocks. The oldest meteorites date to 4.56 billion years ago. Meteorites represent leftover bits from the time of solar system formation and mark the initiation of planetary accretion. The oldest moon rocks from the Apollo missions date back to 4.47 billion years ago, indicating that the moon formed 90 million years after Earth's accretion. There is no rock that old, but tiny minerals called zircons that resist destruction when recycled from one rock to another have been found in the Jack Hills of Australia, dating back to 4.4 billion years ago. These zircons mark that the Earth's crust formed 150 million years after Earth's accretion. The bulk composition of Earth is dominated by 6 major elements: oxygen, silicon, aluminum, magnesium, calcium, and iron far outweigh all other heavy elements in the rocky terrestrial planets. These 6 elements make up 98% of Earth's mass and of the mass of Earth's moon, Mercury, Venus, and Mars. Elements on the periodic table are organized by their atomic weight, meaning the number of protons in their atomic nucleus. Elements 2, 10, and 18 are found in the rightmost column. They are helium, neon, and argon. These elements are found in the hot envelopes of exploding stars, but they never form minerals. That's because they have a full complement of electrons. Their electron shells are complete, so they remain as isolated atoms and typically remain in the gas state unless temperatures drop close to absolute zero, when they can freeze into crystals. Other elements don't naturally have these magic numbers of electrons, so they go through all sorts of changes to gain or lose electrons to obtain 2, 10, or 18 electrons total. That need to achieve a magic number is what drives chemical reactions and forges chemical bonds. The first chemical reactions following the Big Bang produce molecules, which are small clusters of a few atoms tightly bound into a single unit. Hydrogen molecules, H2, each with 2 hydrogen atoms locked together, came first. When 2 hydrogen atoms meet, they pool their resources to form a molecule with that magic number of 2 shared electrons. This sharing of electrons is called a covalent bond, which is the most important type of bonding in all living things, because it's the way the element carbon typically bonds to other elements. This is also how the atoms bonds in water molecules. Another type of chemical bond occurs by transferring electrons, which is called an ionic bond. In metals, a cluster of atomic nuclei float in a sea of electrons. Following the first supernova, as space was seeded with a variety of other elements, many interesting molecules could form. Water, with 2 hydrogen atoms bonded to an oxygen atom, is one early example. Nitrogen, with 2 nitrogen atoms bonded together, ammonia, methane, carbon monoxide, and carbon dioxide molecules also enrich the space around supernovas. All of these molecular species are formed from covalent bonds. When a molecule involves different elements, such as in water, methane, or carbon dioxide, it is called a compound. Nitrogen, with 2 nitrogen atoms, is a molecule, but not a compound. None of these molecules and compounds are a mineral unless they freeze into ice. Two other types of chemical bonding enrich the cosmos. Ionic bonding occurs when 2 atoms exchange 1 or more electrons. An atom is electrically neutral because the positive charge of the protons balances the negative charge of the electrons. An atom that has excess positive or negative charge is called an ion. Ions have filled their outer electronic shell by lending or borrowing an electron from a different atom. When an atom gives away an electron, there is 1 more positive proton than negative electron. So the ion is positive, and we call it a cation. Reciprocally, if an atom received an electron, there is 1 more electron than there is proton. So the ion is negative, and we call it an anion. This is illustrated by the pair of elements sodium and chlorine, the constituents of table salt. In a solution, sodium gives away an electron that is borrowed by chlorine. Sodium becomes the cation Na+, and chlorine becomes the anion Cl-. Metallic bonding occurs when lots of atoms have too many electrons. Metals abandon their electrons to form a giant soup of electrons floating around a cluster of atomic nuclei. Electrons are delocalized, so they are free to move around, forming excellent electric conductors. The atom nuclei become positively charged and attracted to the sea of electrons. We know Earth's composition from various complementary observations. Earth's orbit and interaction with the moon help us understand its total mass. The moment of inertia, which is defined as the resistance to change in rotation, depends on the distribution of mass. Earth's moment of inertia is significantly less than that of a uniform sphere of the same size and mass, which means that significantly more mass is concentrated in a dense core compared to a uniform sphere. We also sample rocks directly, but the composition of Earth's crust is different from that of the bulk because the Earth's core is almost entirely iron and nickel. And because of differentiation, the crust and mantle concentrate lighter and heavier elements, respectively. On Earth, there are 6 dominant elements: oxygen, magnesium, aluminum, silicon, calcium, and iron. Their contribution to the mass of the planet is as follows: iron and oxygen, 30% each, silicon and magnesium 50% each, and a little less than 2% each for aluminum, calcium, and nickel. How these elements combine to form compounds dictates the composition and properties of minerals we find on our planet. Oxygen is by far the most abundant element in the Earth's crust and mantle, as nearly every other atom above the core is oxygen on average. Oxygen currently plays an essential life-giving role, enabling respiration. But oxygen in the atmosphere is a relatively recent development. For more than half of Earth's history, the atmosphere had virtually no persistent oxygen. Even today, with a lot of oxygen in the atmosphere, almost all of Earth's oxygen is locked into the minerals and rocks of the crust and mantle. When you climb a mountain, most of the atoms beneath your feet are oxygen. On a beach, almost 2 out of 3 atoms that support your weight is oxygen. Oxygen is Earth's master electron acceptor. Number 8 on the periodic table of elements, it needs 2 other electrons to get to the closest magic number of 10. This acquisitive urge makes it one of the most reactive, corrosive gases in nature. Oxygen couldn't play such a critical chemical role as an electron acceptor in Earth's outer layers, were it not for several kinds of atoms that are equally eager to give away or share their electrons. In fact, the other 5 elements of the 6 most dominant elements are all electron donors. The most enthusiastic of these electron donors is silicon, which accounts for about 1 in every 4 atoms in Earth's crust and mantle. On the periodic table, silicon is number 14, just below carbon. That means that silicon has 14 protons in its nucleus, which can be balanced by 14 negative electrons. But 14 is not a magic number. 10 or 18, equally distant from 14, are magic numbers. As a result, silicon has to form chemical bonds. Silicon-oxygen bonds are found in almost every crustal and mantle rock, and in the majority of minerals. Minerals with silicon-oxygen bonds are Earth's most common minerals, both in total volume and in the sheer number of different species, more than 1,300 and counting, because more are discovered almost every month. These minerals, collectively known as silicates, are also richly varied in their atomic architectures and in their physical and chemical properties. That's because the silicon-oxygen bond is so versatile in the way it connects with other atoms. Minerals are naturally occurring, inorganic, solid materials with well-defined chemical compositions. The 2 characteristics that best allow the study of minerals are their crystal structure, the way the atoms of the elements are packed together, and their composition, the major chemical elements that are present and their proportions. The most abundant mineral group is the silicates, but other mineral groups include oxides, sulfides, carbonates, sulfates, and phosphates. Oxide minerals are formed when at least 1 oxygen atom is bonded to 1 or more metal alloys. The sulfide minerals contain 1 or more atoms of sulfur. An example shown here is pyrite, Fe(S)2. Oxides and sulfides can have great economic value. There are about 4,500 known minerals on Earth. Some minerals, for example, diamonds and graphite, were created in supernovas. Other minerals formed during planetary accretion. Many more were created by the mixing action of plate tectonics. But perhaps 2/3 of known minerals would not have emerged without life and atmospheric oxygen. As we will see in subsequent lectures, life played a tremendous role in shaping its environment, affecting the composition of Earth's atmosphere and the distribution of elements in Earth's interior.